timer's always running when I'm talking. Okay? Because last class I thought it was running, and then it wasn't running. And then we missed like 10 minutes. So that's why you guys get to be recorded today. So, let's talk. What shape is this? Without even graphing it, what shape is it? Circle? Okay, so we think it's a closed, rounded figure because we see sine and cosine, right? Okay, circles would have these numbers being the same, right? Since those numbers are different, it is an ellipse, or an eclipse, or an eclair. That's the three names that I've gotten so far today. Okay? All right? Which I'm fine with any of them because they all start with E. Okay? Where is the center of my ellipse? We can do this one again without graphing also. At 2, -4. This part right here is my x part of the center. This part right here is the y part of my center. Okay? That's the cool thing about parametric equations, is that whatever's added or subtracted at the tail end of it without the t, that's kind of where that center goes. Okay? And it's straight up. It's not like algebra. If you think back to your parabolas and doing vertex form in parabolas, you had to think one was normal, one was opposite. It's all kinds of confusing. Not with parametrics. Straight up. What you see is what you get. Okay? All right? Now, let's eliminate the parameter. Okay? So, sines and cosines. What's the first thing I think of when I see eliminate the parameter? Sines and cosines. The hammer. Okay? I think of the hammer first. If there's not sines and cosines, then I solve one of them for t, plug it into the other one, get my algebraic expression, or my equations. Okay? So on this one, I have to take x equaling 3 cosine of t plus 2. And I have to solve that for cosine. So first I'm going to subtract 2. Then I'm going to divide by 3. So I get x minus 2 over 3 equals cost. Okay? With me on that. Then I go to y. Y equals 2 sine of t minus 4. Add 4. Divide by 2. So y plus 4 divided by 2 gets me cent of t. Actually, just cent out of t. Okay. Then we said we were thinking the hammer. Knock, knock, knock. Here comes the hammer. Cosine squared of t plus sine squared of t is equal to 1. So that's going to be x minus 2 all over 3, quantity squared, plus y plus 4 all over 2, quantity squared, equals 1. Now, you guys don't have a lot of experience with conic sections, but this is the algebraic form of an ellipse written out like that. Okay? because it's algebra, now I gotta think oppositely when I'm thinking of my center. So that's why my center is at -2, my center is at +2, -4. Okay? And then what an ellipse is it's a stretch in one direction of a circle. So this would tell me then that I would go to that point, 2, -4. And then from that point, I'm going to go 3 horizontally in both directions. And then that's going to be the endpoints of what's called my major axes. Then I'm going to go 2 from that center point vertically in both directions. And that's going to be the endpoints of my minor axes. An ellipse has a major axis, which is the longer one, and a minor one, which is the shorter one. Okay? And then I just draw into my nice little oval. Okay? Good? What? Oh, okay.
I disagree.
Oh, all right. Fantastic. Now, yesterday, at the towards the end of class, we kind of rushed through these a little bit, so I wanted to go over these once again. Okay? We talked about the Ferris wheel problems, and we talked about how in the parametric form of our Ferris wheel, it was x equals r times the cosine of bt plus c, and y was equal to r times the sine of bt plus c, and then we had a d on there also. Okay? And we talked about different tweaks about it. Like d is going to be adjusted based off of how high we are off the bottom of our Ferris wheel is off the ground, and the radius. Okay? D is the radius plus how high it is off the ground. Okay? We talked about that yesterday in that one. We also talked about, well, what would happen to those functions if I switched my direction of travel from counterclockwise, because counterclockwise is my trig direction of travel. That's how we go around the unit circles, counterclockwise. If we switch that to clockwise, what's the one tweak that we have to do to those two functions? Negative b. Yep. We have to make b be a negative number. And that switches my direction of travel. Okay. Then we said, well, what if we start at the top? Yesterday, we started on the right side, because that's 0 on my unit circle. That's 0 in trig, right side. What if we start at the top? What tweak do we have to add? What about pi over 2? So what value in those functions would be pi over 2? C. My C value here, if I'm starting at the top, my C value would be positive pi over 2. Could it be anything else? What do you got? Positive or negative? It could be negative 3 pi over 2. Could it be anything else? It could not be negative pi over 2. That would not have me start at the top. One? No. Think about the unit circle. I want to get more numbers that are up here at the top. Pi over 2 is one. Negative 3 pi over 2 is another one. 5 pi over 2. 9 pi over 2. 13 pi over 2. How am I getting all those? Adding 2 pi. Okay? Negative 7 pi over 2. Negative 11 pi over 2. How am I getting all those? subtracting 2 pi. Yep, exactly. Okay? So as long as I'm at that point on the unit circle, it could be any, you can add or subtract any time or any number of times 2 pi. Okay? All right? What if we now start at the bottom? How do those tweaks get made? Because normal, well, I shouldn't say normal, 85% of all Ferris wheels load at the bottom. Okay? So what would the tweak be on that one then? What do you got? So you said positive 3 pi over 2 or negative pi over 2, right? Okay. Or, again, same thing. We could add 2 pi to those, or we could subtract 2 pi from those, and we get the exact same thing. Okay? All right? Couple of tweaks there. Now, because we love you so much, later on today, we're going to give you a formative assessment that you're going to take home and do tonight. Okay? So let's do another Ferris wheel problem, since wink, wink, nudge, nudge, your formative assessment is a Ferris wheel problem. Okay? All right? So this Ferris wheel has a radius of 60 feet. Now, you don't have to write down every word, but just write down the key stuff. You know what I mean? Like, radius of 60 feet. Period is 12 seconds. Bottom is 8 feet off the ground. Right? Clockwise rotation. And we're starting at the bottom. Okay? So, we need to make our parametric equations. Now, the equations that we need to make, just so you know, I'm going to go off this slide for 1 second, are these two ones up here. That's what we need to make based off of this situation. Okay? So, we start with, both of those started with R. Our radius was 60 feet. Or is 60 feet, I should say. Right? Then, x is cosine, y is sine. We're going to kind of build them at the same time because a lot of the stuff happens in both in the exact same spots. Right? Okay? Now, next is our b, right? Is b going to be positive or is b going to be negative? If I'm going in a clockwise direction, b is negative. So both of these have to be negative. Then, the actual b number I get from my period. And yesterday, we said that the period was equal to 2 pi over that b value. I don't know, it stopped in that exact same spot last time too. All right? So to bring to bring the internet up to speed, I wonder if my elbow hit it or something like that. Okay? So it's negative, the negative b because of the clockwise direction. The period we're figuring out right now. Period is equal to 2 pi over b. So 12 equals 2 pi over b. So b is equal to 2 pi over 12, or just pi over 6. Right? Okay? So that gives me my, we'll go up there, negative, whoa, whoa, whoa! We're getting all funky. Pi over 6, pi over 6. Yes? Okay. Anything else that has to be done with the period? Any other values based off of that 12-second period? What? Yes? No? Maybe? Nope, that's later. That's later, yep. All right, let's table that one, because there is one more, but we'll get to it in a little bit. Okay? So then I need t values in there, right? Because where are we starting? At the bottom. So I could either do, so here I could either add 3 pi over 2 or subtract pi over 2. Either one, doesn't matter. If you instead of wanted to go plus 3 pi over 2, that's fine. Just you can't go plus pi over 2 and minus pi over 2, because then you're going to get all kinds of funkiness. Okay? They got to be the same sign. Okay? So we're good there. Did we use all of our information?
Would you add 68?
How did you come up with 68? And where would I add it?
To the sign, and then since it's 8 feet off the ground, and the radius is 60.
So then that gives me my center at 0, 68. So really I'd add 0 to the x, but we don't write that. And then add 68 to the y. Love it. Good catch. Okay. Am I done with my parametric equation? What am I missing? The t values. Okay. So what t values do I want this to go? Remember, t being, in this case, time. I want to make a complete circle on my graph. So what t values would I need? 0 to 12, because I need to start at 0, and I need to finish at 12, because that gets me all the way back around. Yes? Okay. Now, what I'd like you to do, graph that thing. It's a parametric graph, so I have to switch that over to parametric. Okay. No offense, I'm going to go type on my computer. 60 cosine of negative pi over 6 t minus pi over 2 60 sine negative pi over 6 t minus pi over 2, then plus 68. T's to 12. That's it, right? Enter, row. Now, let's think some logic here. This vertical line right here signifies to me that that's my y-axis, correct? Which means then that if I look over this way, that is how far? 60 feet to the left, right? Or negative 60 on my graph. This would be 60 feet to the right, correct? Well, on my current graph, I'm only going 10 feet to the left and 10 feet to the right. So I'm going to have to change that. Okay? So let's go into my menu, and let's go into my window. Okay? Now, I'm going to walk you through how I come up with the different windows that we look at. Okay? So I need to go 60 in both directions to get to the edge of my Ferris wheel. So I'm going to go, I like to see a little bit more, I'm going to go 80 left and 80 right, which means I want to go with a scale of 10. Okay? You could go automatic on your scale, but I like to know what my scale is so that I can know and I can kind of predict where things are. When my scale is automatic, I don't know what each dash is. So that's just me. That's how I roll. Okay? Y's now. On my Y's, I need to go from ground level up 8, then up 60, then up another 60. So I need to go from 0 up to 128. So I'm going to go -10 up to 140, and I'm going to go by tens. Because that gives me room on both top and bottom for me to see what's going on. Now, what's the downfall with that? It's not really a circle, is it? Okay? All right? So, since it's not a circle, then I'm going to use my window, and it's B, it's down here. It's zoom square. And by hitting zoom square, it squares up my display and makes it look like a nice circle. Okay? But now what's the downfall? Now I don't see the whole thing. So now I'm going to grab onto my axes and pull down on it. And that allows me to see my whole thing. Now, in the last class, they were asking, what's this funky little line down here? Well, that funky little line down there is just the part of your function that we can just get and move out of there. Okay? Did you find it? Didn't show up? Let me see your function. You forgot the t inside. -pi/6 times t in both cases. Okay? Now, from this, we can ask some questions. A question that we could ask is, what is the location of the gondola at 5 seconds? What is the location at 47 seconds? Well, we can go back in here, and now we can trace our gondola. I'm going to set my trace step at 1, because then it's going to tell me every second where we're at. Okay? All right? And then I go back into menu, back into trace, and then now I can trace this all the way up to and including t = 5. Okay? So I can go, oops, see there's my motion. I can animate mine because the software is a little funky. So I'm moving in a clockwise motion. But now let's get it to, oops, I got out of it. Trace, graph trace. I want to go at 5. Okay? So there's my location at t = 5. I'm 30 feet to the left of center, and I'm 120 feet above the ground. Okay? 47 seconds was the next one. Okay? How am I going to figure out where I'm at 47 seconds? 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, right? I could keep going down around, right? Or what?
There's 12 seconds in everyone, so you
Subtract 12, right? So 47 minus 12 would be 35. Minus 12 would be 23. Minus 12 would be 11. So I really want to know where I'm at t equals 11. And I'm right there. Okay. So at 5 seconds, I'm 30 feet, whoa, tap the brakes. I'm 30 feet to the left of center and 120 feet up. At 47 seconds, I'm 30 feet to the right of center and 16 feet up. Once in a while I do answer myself too. Okay, so this is at t equals 5, and this was at t equals 47. Okay? Now, a new wrinkle to this Ferris wheel type problems is how far have we traveled if we're traveling on our Ferris wheel for a minute. Okay? So there's a couple of things involved here. So in 1 minute, how many revolutions do we make? 5, right? Because I take my time and I divide it by my period, and that's going to give me my revolutions. So 60 seconds divided by 12 seconds is 5 revolutions. Logic tells me that my gondola is on the outside of that circle, or of the Ferris wheel, I should say. And as I go around, that makes a circle. Well, how far do I travel in 1 revolution? What part of a circle am I traveling along? What part of the circle am I traveling along? Somebody just whispered it, I heard it. I'm traveling along the circumference. So 1 revolution is 1 circumference What's the formula for the circumference of a circle? 2 pi times the radius, right? So that's 2 times pi times 60, which is 376.99 feet. So in 1 minute, I make 5 of those revolutions, correct? So my total distance is going to equal 5 times 376.99 feet. Oops, there's an F in feet. Okay. Which is 1,884.96 feet. So that's the total distance that I traveled by spinning around the Ferris wheel for 1 minute. Okay? Alright. Good times. Good times. Alright? So, now, let's talk our second style of motion in a plane, and that is we're going to take an object and we're going to throw it vertically in the air. Okay? So what's going to happen, now this is provided there's no wind, no other factors, we're throwing it in a vacuum, okay? The only factor that we have is gravity, okay? Throw it up, it comes back down, and it follows in that same path, right? Okay? So as you go on in mathematics, you will get to a point where you will actually derive this formula. You'll come up with this vertical motion formula. If you do it here at Wausau West, you will actually do it next year in AP Calc. Okay? If you are moving on to someplace else, you will probably do it in a calculus class if you choose to take one down the road. Okay? There are 3 components to a vertical motion function. Okay? The first component is you have your initial height. Okay? How far off the ground I am is going to depend on where I throw this roll of tape from. If I throw it from the ground, that's going to be a different height than if I threw it from on top of West. Okay? The next component that you'll have to deal with is this V sub 0. And V sub 0 is my initial vertical, hence the V, velocity. Okay. What's the third component acting on my object as it's flying? Gravity. And this negative 16t squared comes out of the gravitational constant. Okay? It's actually the derivative of the gravitational constant, okay? Because the change of your rate of change is changing. Okay? So it's the acceleration that's happening when you're with what's going on. Okay? So you're accelerating at a lower rate than you are. Okay? Right? Your rate of change is changing. Okay? And again, you'll explore more of that in calc. Most of you have already used this formula at some point in time because you came through Algebra 2. We did a couple of questions along that, or a couple of days worth of work on this in Algebra 2. A lot of you have done it in science classes out there too. Okay? So, let's dive into a situation now based off of that. So we got the motion of a ball. So, from the top of a building, okay, so you're standing at the edge of the building and you hold your arm out, so your arm's over the edge of the building, and you throw a ball up, so it's going to go up, and then it's going to come back down, and it's going to hit the ground. Okay? Which is different than if I was standing in the middle of the building. Because if I throw it up and it comes back down, it's going to hit at my feet. Okay? Which is going to be 30 feet in the air. Now I gotta get down. I'm old. I'm not used to being climbing around on stuff anymore. Okay? Alright? So, this scenario says that you're on top of a building, and that building is 30 feet up. You take your ball, you throw it up, it goes up, and it comes back down, and it goes splat. Okay? Follows the same vertical motion. Okay? Algebraically, let's figure out what our function S of t is. So S of t is going to be what? Negative 16. That stays constant. T squared plus 50 t plus 30. Huh? Right? Now I can use that algebraic function, and I can say at t equals 0, I can plug 0 into that function, and I can say that that ball is 30 feet in the air. Right? Because I'm launching it 30 feet in the air. Okay? At at t equals 1, that would be what? 64 feet in the air. Okay? So in the first second, it goes up 34 feet. Right? Okay? And so on and so forth. Let's graph that function. So if I graph this function, so I can see the height of the ball, let's start a new graph, and it's just going to be a regular old function. -16. Can I use t? I got to use x because it's a regular algebraic function. X squared plus 50x plus 30. Right? Shabam. Okay? What can you tell me about the ball? Tell me everything just from that picture that you know about the ball. What do you got, Jack?
Travels up for some time and then stops traveling up and then goes back down.
Okay. What else? Okay.
It's probably lower than it started.
What do you mean it's probably lower than it started?
Like because you started at 30 and then you threw it down.
Okay. So what is the x-axis represent in this one? But what does it represent? It represents the ground, right? Because that's a height of 0. Right? Okay. So this is the ground. So do I even care about anything down here? Like, whoa, whoa, whoa. Hey now. What was going on there? Do I care about anything down in here? No, right? Do I care about anything over here on the left side of my y-axis? No. So let's get rid of those. Okay? So let's go into our menu. We're going to change our window. I want to go -1, 2. How far out do I need to go? 6? How far out do I need to go? When's it going to hit the ground? 3.5-ish? Okay. All right. So 4. Let's go 5. I like 5. 5's a good number. And I'm going to go by a scale of 1. Again, I like to know what my scale is. Okay. Y's. Do I need below ground? No. But do I want to see the ground? Yeah. So I'm going to go -10 there. Okay. Now, how high do you think that ball's going to go? Well, no, remember I'm launching it at 30. And we said after, if I put 1 into my function, I'm at 64. 80? Okay, let's try 80. And I'm going to go by tens. Ho, look at that. That's a thing of beauty. That's a beauty. Now, if I trace that, I can go, I'm going to go over here to my computer because it makes it go a little easier. I can start there. Bam. That's my height that I threw it up at, right? I launched it 30 feet in the air. Then, it's traveling upwards, correct? And it gets to a maximum height of 69.1 feet. 1.56 seconds after I released it. Then what happens? It starts to fall. And it's falling. And it's falling. And it's falling. And it's at 3.64, we have a 0. Okay? Okay? Now, is that the true path of my ball? No, because what is that graph representing? If I labeled my axes, it'd be height up here, and it would be time down here, right? Okay? So that's not the true path of my ball, because my ball is following in that exact same, I'm throwing it straight up, and it's going to come straight back down. So in like 1.5 seconds, I better pull my hand back, because otherwise it's going to hit my hand. All right? So we can use parametric equations to model the actual flight of the ball. Okay? So let's set up a parametric equation based off of this scenario. My question to you is, the x part of a parametric equation, no, I haven't been able to do this yet today. Oh, snap, I finally did it. Yes. That's the first time in 3 hours that I've been able to do that. What? Yeah, 3 hours of practice. Okay? The x part of a parametric equation is my horizontal movement, correct? Is this ball moving horizontally? No. So this x can be any number. It's not going to change. So what do you want it to be? 5? I like 5. If you don't like 5, make it be 7. If you don't like 7, make it be anything but 0. Because why don't we want 0? Because that's right along our axes, right? Okay? So we don't want 0. So make it be any number but 0. Okay? The y part. What's the y part of a parametric equation? That's the vertical motion, right? So that's my negative 16 t squared plus 50 t plus 30. What's the only part that I'm missing? The t, right? Okay, so my t values are going to run from 0 to, when does it go? Splat. Gets you every time, doesn't it? When does it go splat? 3.64. All right? Let's make that bad boy now. Okay? So now I got to make another page, a graph. I want it to be a parametric. Whoa, tap the brakes. Whoa, tap the brakes.
It's freaking.
It's working. Okay? We said 5 there, right? Or any number we wanted there. And then we said negative 16 t squared plus 50 t plus 30. And then I want to change this to be 3.64. Yeah? Jingle, bam. Uh-oh. Where is it? Got to adjust our window again, right? Okay. So, window settings. X's, I'm going to go -1. We're going to go up to 7 because we had it at 5. I'm going to go by 1s. Minimums. So this was -10 to 80 because our maximum height was 69.1. And we're going to go by 10s there. Jingle, bam. There it is. Now let me get this out of here. Actually, we can go with this up here because we can see it then. Okay. All right. Now, trace that thing. Work for me. There it goes. There it goes flying, right? So here, now the ball's coming back down, hits flat. Starts at 0, goes up, gravity, comes back down, splat. and it's in that vertical plane. Okay? So this is the true flight of the ball. Now, let me, 0.8, so we need to go up. Let me go over here. Move it. It's a software glitch on my computer. Yours doesn't do that. I know, it sucks, because that'd be pretty cool. Okay? So at 0 seconds, I'm 30 feet in the air. Does that make sense? Yes? Yep, that makes sense. And then what was it? 1.5 got me to the top. So 1.5 seconds. I'm at 69.1 feet. Then we said at 3.64 seconds, we went splat. Don't worry, Obi, I won't splat it for you again. Okay? Okay? Now, why isn't it exactly 0? Trick question. Well, it kind of is, right? But why isn't it exactly 0? You got when you hit it, you walk away. You know what I mean? Do you know why? How do we get 3.64? It's rounded, right? So it's rounded a little bit. So that's that rounding error part there. Okay? And there we go.